You ever wonder how a brand new website just appears on Google, sometimes only hours after it goes live? It's not magic, right? It's actually the work of these tireless little digital explorers. You can think of them as robotic spiders that are constantly mapping the huge, ever-changing internet. So today, we're going to do something pretty cool. We're going to design one of those bots ourselves, right from scratch, and really dig into the blueprint that powers the whole modern web.
All right, so here's our game plan for this little Build-A-Bot project. First, we'll figure out what a web crawler even is. Then we'll get into its workflow, teach it some good manners, figure out how to make it handle the entire internet, and finally we'll make it smart enough to avoid traps and be ready for whatever's next.
Okay, so let's start at square one. What exactly are these hidden robots that are out there, trying to make sense of the digital chaos?
Yeah, let's go right back to that first question. Imagine you just launched your brand new blog, or maybe an online store, and bam, seemingly out of nowhere, it's showing up in search results. How does that even happen? Well, the answer is exactly what we're talking about today.
And here it is. A web crawler, sometimes called a robot or a spider, is really just a program. Its whole job is to browse the web automatically. That's it. It just follows links from one page to the next, discovering and indexing all the content it finds, so that big systems, like search engines, can actually find it later.
And why would you build one of these? Well, the reasons are huge. I mean, think about it. Search engines, obviously. Google's Googlebot is probably the most famous one. But it's not just them. The Library of Congress uses crawlers to archive our digital history. Financial firms use them to mine data. You even have companies using them to monitor for things like copyright infringement. They are absolutely fundamental to how we find, well, anything online.
And at its core, the basic algorithm sounds almost laughably simple. Okay, step 1, start with a list of URLs. Step 2, download those pages. 3, pull out all the new links you find on those pages. 4, add those new links to your to-do list. And 5, just repeat that, over and over, forever. Sounds easy, right? Well, as you're about to see, that simple idea gets really complicated really fast.
Okay, let's dive into the next part, the crawler's workflow. This is the actual blueprint. How do we take that super simple loop and turn it into a real, robust system that actually works?
All right, here we go. This is the high-level design. I know it looks like a lot of boxes and arrows, but don't worry. The best way to think about it is like a sophisticated assembly line, but for processing URLs. Let's just follow a single URL on its journey all the way through this thing. Okay, so the journey starts with what we call seed URLs. These are just our starting points. These seeds get fed into the URL frontier, and you could just think of the frontier as our bot's master to-do list. It's what keeps track of all the places we still need to go. From that to-do list, a URL gets picked up by the HTML downloader. Its job is simple. Go fetch the actual web page. Then it immediately gets handed off to the content parser. And this is basically our quality control step, making sure the page we just downloaded isn't broken or junk before we waste any more time on it.
Now, this next step is so important. And here's why. Get this. Some research shows that almost 29% of web pages are just duplicated content, nearly a third. So to avoid wasting a ton of time and space, we have this crucial checkpoint, content scene. It basically asks, hey, have we already processed this exact page before, even if it was at a different address? If the answer is yes, we just toss it. No need to do the work twice.
But if the content is new, we get to the really cool part, the feedback loop. The link extractor jumps in and pulls out every single hyperlink on that page. Each of those new links then gets checked against our bot's memory. URL seen? To see if we've come across that address before. And if a URL is totally new to us, it gets sent all the way back to the beginning, right into our main to-do list, the URL frontier. And that right there is the magic. It's the self-perpetuating cycle that lets this thing just go and explore the web all on its own.
Okay, so we have a working bot, but a powerful bot can also be a really annoying one. So we have to teach it some manners. This is our politeness protocol, and it's all about making sure our bot is a good citizen of the internet. So here's the problem. Imagine our crawler lands on a page with, say, 1,000 links, and they all point to the same website. A simple, dumb crawler would just try to download all of them at once. And to that poor website server, that looks exactly like a denial of service attack. It looks like you're trying to crash their site. We absolutely cannot have that.
The solution is actually really elegant. Instead of having one giant to-do list, we break it up into lots of tiny ones.
We use a queue router that says, okay, all these links for wikipedia.com, they go in this special Wikipedia queue. Then we assign one worker to that queue, and it just politely downloads pages one by one, maybe even with a little pause in between. No more flooding.
But just being polite isn't enough. We also want our bot to be smart. I mean, not all pages are created equal, right? A link to Apple's homepage is probably a bit more important to crawl than a link to some random comment on a forum from 10 years ago. So we add a prioritizer. It looks at the URLs coming in, gives them a score, and shuffles the more important ones to the front of the line.
All right, our bot is polite, it's smart, now let's make it powerful. How in the world do we take this program running on, say, a laptop and scale it up to handle the entire internet?
Just to give you an idea of the scale we're talking about, our goal is to collect 1 billion pages every single month. Yeah, a single computer is not going to cut it. This forces us to think about performance in a totally different way.
So to hit that number, we need a whole playbook of optimizations. We have to distribute the crawl across tons of machines. We need to cache DNS lookups so we're not constantly asking, where is this website? We can even be smart about locality, placing our servers geographically close to the sites they're crawling. And finally, short timeouts. If a server is slow, we don't wait around. We just move on.
But out of all of those, the real game changer is the distributed crawl. It's the most important technique by far. Instead of just one downloader, our URL frontier acts like a dispatcher, sending jobs out to a whole fleet of hundreds, maybe thousands of machines. This is how we go parallel. This is how we achieve that massive internet-level scale.
Okay, for our last section, we need to talk about some real-world problems. We need to make our bot robust enough to handle the messy, wild west of the web, and also flexible enough so we don't have to rebuild it from scratch in a year.
You know, the web can be a tricky place. It's full of these things called spider traps. These are pages that are basically designed to get a crawler stuck in an infinite loop. You know, like a calendar that has a next month link that just goes on forever. Our bot needs to have some smart rules, like setting a maximum length for a URL, to spot these traps and know when to just walk away.
And finally, a great design has to be extensible. What happens when, tomorrow, we decide we want to download not just web pages, but maybe PNG images too? Well, with a good modular design, it's no big deal. We can just build a little PNG downloader module and plug it right into our existing system. No need to tear the whole thing down and start over.
And that really brings us to the future, doesn't it? We've designed a bot that's fantastic for a web made of HTML pages, but the web is changing fast. We've got AI-generated content now, complex web applications, even entire virtual worlds being built. So I'll leave you with this question. How does our robotic explorer need to evolve to be able to map those digital universes of tomorrow?